All right, so a really important piece of using and thinking about and solving a partial differential equation, complex differential equation like the heat diffusion equation, is understanding what's happening at the surface. So the heat diffusion equation is telling us how heat moves around inside of objects, but we also need to understand what happens at objects' surfaces. So that's the boundary conditions. There are a few common boundary conditions. We could have the surface of our object be a constant temperature. So have it locked at, say, a temperature Ts, and then change inside. We could have a constant surface heat flux, an insulated surface, which is similar to that, or we could have something like convection at the surface. We can have other things as well, but not things that we'll attempt, at least analytically. So let's see what these would look like as boundary conditions. Constant surface temperature, what that would mean is the temperature of our object's surface is held at 50 degrees or 10 degrees or something like that, and it's just held at that one constant temperature. What that's going to look like mathematically is the temperature at a position, here at this location, x equals 0, or maybe it's at a different location, x equals L, wherever that location happens to be, at all times t equals just some number. In this case, I'll say it's the surface temperature. Fairly straightforward, easiest boundary condition, easiest one to apply and think about. This next one, a constant surface heat flux, is quite common in the real world. This would be something like a, could be like electrical heater. Where we have a continuous, 20 watts of heat going into our object, and we're going to see how that heats up the system. What that does is gives us a constant slope in the temperature gradient, in the temperature here at the object's surface. And that slope is equal to that heat flux, so minus the heat flux divided by the thermal conductivity. And throughout that entire process, whether the object is heating up or cooling down, this slope remains fixed when we have a fixed heat flux. So the way that we can write that as a boundary condition is this number is equal to a constant, and that equals minus k dt dx, right? That's just the law of conduction, evaluated at our surface location. In this case, we'll say that the surface is at 0. So that is the slope there at the surface. So an insulated surface is a special subcase because often we can have surfaces, sometimes even in the middle of objects, as we'll see, where effectively a surface is insulated. This, we see the same equation, but now Qs double prime, the heat flux is equal to 0 because it's insulated. So what this means is 0 equals minus k dt dx, evaluated at x equals 0, or just the slope of the temperature is equal to 0. Right, 0 because we can just cancel out k. And 0 equals the slope of the temperature evaluated, again, at that surface. So you can see here, right, the slope here at the surface, as is shown, is 0. It's flat. last one that we're going to consider is convection. And in this case, the heat transfer at our surface is not zero. It's not a constant. It's governed by Fick's law, by Newton's law of cooling, by our convection equation. So Q double prime of our convection equals minus K dt dx at x equals 0. And again, where these equations are coming from, I'm just simply doing an energy balance at the surface and saying that the heat coming into one side of the system, so the heat flowing here, is equal to the heat that's flowing there. Because they have to be equal because the heat didn't disappear as it went from left to right. So that's all that I'm saying. That's where these equations are coming from. So my convection here on the outside of the object is equal to the conduction that's happening just on the right side of that surface, just on the inside of that surface. I can go a little further because I know what convection looks like, and I can say that this is the convection coefficient times the temperature of the fluid minus the temperature of the surface, and that equals minus K d temperature dx evaluated at x equals 0. So we have a couple different boundary conditions, right? An insulated surface, a constant surface temperature, a constant surface heat flux, and a constant surface temperature. And we're going to see how we can take all of these different boundary conditions and use them as we're solving our heat diffusion equation.